Fit is a very important thing we need to talk about. Fit is when objects come together. So if you have two or more objects that come together, they fit. Think about when you're driving and you want to park a car, you have to fit your car between the spaces between two other cars. So the dimension is called the nominal space or the nominal dimension. That's where you normally would want to park, is between the two lines. And then you park, and hopefully, if you park well, you're parking in the middle. And if you park in the middle or wherever you park, you're going to have some clearance, which means a little room between you and the line or you and the car next to you. So fit is about how objects fit together, how they come together, and we want to know basically what kind of clearance there is, and the clearance is the empty space between the parts. We want to know what kind of fit. So it's very important that when we put objects together, we describe how objects fit. And sometimes you want a loose fit with pliers. You want the pliers to move back and forth. You don't want them to be stuck. So you want a loose fit with high clearance, lots of space in the bolt that holds the pliers together. Or sometimes you want a very tight fit. So for example, if you're fitting a wheel onto an axle, you want to make sure that when you turn the axle, you also turn the wheel and there's no slipping. There's no slipping of the wheel. So you want a tight fit with little or no clearance whatsoever. When we talk about parts fitting together, we talk about mating parts, which are parts that come together. They're meant to come together. They're designed to come together. For example, a lock and a key, or two gears that are meshing together, a nut and a bolt, or in our case, we're going to talk a lot about holes and shafts. So these are all mating parts. So for example, with a hole and a shaft, we have basically three ways to talk about how holes and shafts fit together, or three ways of describing fits between holes and shafts. We could have a loose fit where there's a lot of room between the hole and the shaft. We could also have a slightly loose fit where there's a little less room, a little less clearance between the hole and the shaft. Or we could have a tight fit where there's not much clearance or maybe no clearance between the hole and the shaft. And sometimes we want this if we want the parts to stay together. We talk about three kinds of fits in engineering. The first kind of fit is called a clearance fit, and that's when the maximum shaft diameter is always smaller than the minimum hole diameter, which means the shaft basically is always smaller than the hole, so there's always clearance. There's always room for the shaft to move in and out. Then there's the interference fit, where we have the shaft is always larger than the hole. The maximum, or I should say the minimum shaft diameter is always larger than the maximum hole diameter. So the shaft never really fits in the hole, and therefore you have a very tight fit. And then in between, you have a transition fit. And that's where there could be clearance or there could be interference. So there could be a case where the shaft slides in and out of the hole easily, or a case where it gets stuck in the hole, or you have to force it into the hole. So for example, in the clearance fit, you have lots of room between the hole and the shaft. That's your clearance. Or in an interference fit, you have the shaft is larger than the hole, and sometimes you have to hammer it in or pound it in because the hole and the shaft interfere with each other. They interfere with each other, so the shaft does not go in the hole very easily. So you may have to force it in or pound it in. With a clearance fit, again, we have the shaft and the hole, and the shaft fits easily inside the hole. There's lots of room. But also we know that a shaft can have a tolerance, which means the shaft could be larger or smaller. And a hole, of course, has a tolerance. So we have a hole and a shaft. The hole has a plus or minus C tolerance, or a plus C or a minus D tolerance. and the shaft has a plus or minus A tolerance, or a plus A and a minus B tolerance. Now we can represent these tolerance zones as rectangles. So the shaft has a tolerance zone and the hole has a tolerance zone. And if we pull those out, we can compare the two. So here's the shaft tolerance zone. It has a plus A and a minus B tolerance. And of course, the hole has a plus C and a minus D tolerance. So these are the shaft tolerance zone and the hole tolerance zone. And we notice that between the two is the clearance, which is always greater than 0. That's why we have a clearance fit. The shaft is always smaller than the hole. No matter how large the shaft gets, no matter how small the hole gets, there's always room between the two. There is always clearance. Well, what if the D tolerance is 0 for the hole? Well, we have still the C tolerance, the plus tolerance, so the hole is still slightly bigger, but it doesn't get any smaller than what's called the nominal. And we call this the 0 line. So the 0 line is where one of the tolerances is 0. And the shaft, which must be smaller than the hole, can be represented below the 0 line. So here's the shaft tolerance zone below the 0 line, and the hole tolerance zone is at and above the 0 line. And the space in between, of course, is the clearance. So we have a little bit of clearance left over. That's why we have a clearance fit. We have room for the shaft to move in and out of the hole. We call this the hole basis system. So whenever one of the hole tolerances is 0, and whenever exactly when the lower tolerance is 0, we call that the hole basis system. Well, what if one of the values of the shaft tolerance is 0? Well, again, we can draw the shaft tolerance zone, and we'll make the A value 0, which means the shaft only gets smaller. It only decreases in diameter. And then we draw our 0 line, which is where the shaft tolerance is 0. And of course, the hole is always going to be larger than the shaft. So we have to put the hole tolerance zone above the shaft and above the 0 line. And again, the space in between is going to be the clearance. Whenever we show the hole tolerance zone and the shaft tolerance zone in this way, we call this the shaft basis system. So this is another way of showing the same thing. So notice that the clearance stays the same, and both situations are the same. So these are two ways to get the same result. We can either talk about the hole basis system, where one of the hole tolerances is 0. In fact, we talked about the lower tolerance being 0, or the shaft basis system, where the upper tolerance of the shaft is 0. But either way, you can describe a fit, in this case a clearance fit, with one of these two methods. With the interference fit, again, we have a shaft and we have a hole, and because they interfere, the shaft is larger than the hole. Also, of course, the shaft has a tolerance. It's either plus or minus A, or plus A and minus B. And the hole also has a tolerance, plus or minus C, or plus C and minus D, which means that we can also describe a shaft tolerance zone, and we can describe a hole tolerance zone. And we can look just at the tolerance zones. We have the shaft tolerance zone, plus A, minus B, and we have the hole tolerance zone, plus C minus D. And the difference between the two is called the interference, which is always more than 0, which means the shaft is always greater than the hole. This is why we call it an interference fit. The hole and the shaft interfere with each other. The shaft is too big for the hole. Well, what if, again, one of the hole tolerances is 0? So, for example, the D value is 0. So the lower value of the hole tolerance zone is 0. Well, again, we can draw the hole tolerance zone with D equals 0. We can draw a zero line, which is where the tolerance is 0. And we know that the shaft zone has to be higher than the hole because the hole is smaller than the shaft. The shaft has a larger diameter than the hole. And of course, the difference between the two is how much the hole and the shaft interfere. So that's how much interference there is. We call this, again, the hole basis system. So anytime the hole tolerance zone has 0 for its lower limit, its lower tolerance, then we call that the hole basis system. And this is one way of describing an interference fit. Well, what if the shaft has a tolerance value that is 0? For example, if A, which is the maximum tolerance, is 0, how do we describe this? Again, we draw the shaft tolerance zone with the upper tolerance equal to 0. We draw in our 0 line, and we know that the hole must be less than the shaft because this is an interference fit. So the hole tolerance zone is below the shaft tolerance zone, plus C minus D, and in between is the interference, is how much the hole and the shaft interfere. Whenever we describe an interference fit like this, we call this the shaft basis system. But either way, the interference is the same, both situations are the same, and there are two ways to get the same result. So we could describe the interference fit of a particular shaft and hole using either the hole basis system or the shaft basis system. Now we say that the shaft and the hole interfere with each other, and they interfere sometimes so much that force is often required to push the shaft into the hole. And the advantage is that when you force the shaft into the hole, the two parts will stay together. And for example, as we said before, if you have a wheel and an axle, you want the wheel and axle to turn together. So it's best when they both interfere, they are forced together so they stay together. And there are many other examples where you want two parts to stay together. So that is why you would prefer an interference fit.